top of that, there are additional constraints, which is it's not only thinking or forces us not only to think how can digital technologies help us to improve performance or drive profitability, but also to do it in a safe manner. This is just an example from the UK where we have direct evidence of environmental concerns, environmental regulations having a clear impact on the ability to operate a particular subsurface operation. In this case, it was about hydraulic fracturing, but fundamental hydraulic fracturing doesn't differ too much in terms of from CO2 storage in the sense that we are trying to inject a fluid in the subsurface. In hydraulic fracture, we are intentionally attempting to create a rupture of rocks, whereas in CO2 storage, one of the things that you're trying to prevent is that unintentionally creating something like a hydraulic fracture. And we also see the regulatory framework of something like what we have in the UK and Europe also maturing across the rest of the world. So it is not unlikely that in the very near future, a mature global regulatory framework for subsurface integrity is going to be a hard constraint on how we see the or how we operate injection sites across the world. Fortunately, in the industry, whether it's been known or not, a lot of the effort in subsurface modeling already goes in terms of attempting to ensure that whatever we do in the subsurface, which is primarily trying to discover and produce hydrocarbons, is actually done in a safe manner. The discipline that deals with this concept is geomechanics. It's a growing discipline in the E&P sector. And if you actually just see from our surveys from 2014 to 2018, I have 3 topics here within the discipline of geomechanics that have a direct mapping to what is needed to safely store CO2 on the ground. And those are the topics related to fault shield and fault reactivation, caprock integrity, and for example, explicitly gas storage integrity. If you see from 2014 to 2018, these topics that were in the 30%, 25% of priority list of what is it that one does in an operator for geomechanics, you see them going up in the rankings gradually. And we're going to see that trend as we go into the future. Now, how is it that nowadays we are addressing this problem? As I said, geomechanics is a discipline that within the subsurface domain in the E&P sector that deals with ensuring that whatever operations we want to do while attempting to discover and produce hydrocarbons, this is done in an effective and safely manner. A lot of the safety considerations that we're after when producing reservoir, it's because safety, it's pretty much related to operational efficiency and cost savings. I mean, nothing is as expensive as an environmental hazard for an oil field. So the main driver, it is cost reduction, and this is why we attempt to model these systems. And for example, what you see here is we have a subsurface model where we have geological faults, where we attempt to study whether the injection conditions are such that, for example, differential pressures across different fault blocks can cause a reactivation of the fault and generate a leakage path for the injected fluids. In the same way, we try to understand the stress state in the subsurface so that once we are injecting, we can verify based on our numerical solvers whether we are inadvertently creating a hydraulic fracture, which is pretty much the same thing as fracking. So this is a big topic, and we have a lot of technologies here. However, we also, even for within the E&P industry, we already see a lot of limitations in the way that these models are being deployed. These models are being scaled, and some of those lessons learned are actually going to be crucial once you go to the CO2 storage market, where you won't have the profit margins, you won't have necessarily the operational efficiency incentives that you might get when thinking about hydrocarbon production. So unless you take the lessons, or unless we take the lessons learned from what we do in oil and gas, it's going to be very difficult to also scale subsurface integrity applications in the CO2 storage market. One of the big lessons learned that we want to convey from many, but one of the important is 50% of the time in doing these studies with these technologies that I just showed you, actually just go into collecting, cleaning, organizing data. Um, not to say that the data is in its nature scarce, but just making sure that we have the correct data. It's in a timely fashion. That we have the correct version of it. It's one of our biggest impediment for the scaling up of this discipline. This has a consequence that we pretty much estimate that over 80% of all wells are actually drilled without a proper geomechanics study. And less than 30% of field development plans include geomechanics. And geomechanics, as I said, is a discipline where we're just trying to make sure that we systematically study everything that's happening in subsurface to ensure that it's operationally safe and also environmentally safe. And as I said before, this is all within the context that the E&P sector has traditionally had very healthy profit margins. And we can imagine that if we don't fix these deficiencies, how is it that we're going to be able to do this in the CO2 storage industry? So really what we need to evolve to this topic to this concept of a digital twin. The digital twin per se it's just a particular label that's not too dissimilar to what we use in nowadays or have we used historically for subsurface models. But the difference in what the vision is that the relationship between the subsurface model that allow us to understand what's going on and whether we're doing things right and the data does not have intermediate steps that are human dependent. So right now, let's say that we want to enable a vision like we have in front of us, where we have seismic data monitoring, for example, the occurrence of microseismicity, or we have this deformation that we can sense through satellite data because of the injection of CO2. All this information, let's say grabbing it, trying to put it inside a model, trying to understand what's happening to the subsurface, there is an innumerable number of steps where you need a human in between. And so really when we talk about digital twins, it's nothing more than what we do today, but trying to reduce the number of links which are dependent on a human. And now to able to achieve that, we need to think about what is the nature of subsurface data compared to the traditional type of data we use when people think about digital transformation. And I'd like to use this example. So when you think of IoT, Internet of Things, and trying to sense what's happening to, say, a rig or any surface facility where you have direct control over where a sensor is and hopefully what the sensor is sensing, everything that you need to focus on is trying to interpret what the sensor is telling you about the system and trying to develop diagnostics and predictive algorithms on top of the data. But really understanding what generated the data is not the issue. I mean, you know that it was, for example, this rig that generated the data, and it's really an analytics and diagnostics problems primarily. But if you think about the subsurface, it's kind of different because your system simultaneously trying to understand what the data tells you and at the same time what generated the data. And why is that? Because we're usually working with data of the subsurface and we can't see the subsurface. We can't touch it, we can't interact with it. And a lot of this, what we're trying to do is first trying to understand what's down there, what is it that is generating the signals, so later we can try to interpret the signals. So this leads to a fundamentally different type of problem, which it's more related to the realm of inversion and uncertainty. In inversion, in the sense that we're trying from the information that we have, just trying to recover what is the most likely system that's generated that information. So for example, we could have, this sensor that here we could have interpreted that it was a small rig, that was a larger rig, or it wasn't a rig at all. And depending on what's that hypothesis that we think that we have in the subsurface, then the way that we would interpret that data is different. And that brings different sorts of demands of how is it that you need to adapt your workflows to operate on the system if it is true that we are going to achieve digital transformation for subsurface and, for example, for CO2 storage workflows. Also, we need to understand the modeling targets. What is it not only from a data point of view, what is it the sort of topics that we need to be able to understand? And that pretty much translate into being able, as I said before, to have accurate representations of subsurface information in a timely manner. So that data is accessible all the time and we're not dealing with versions. Be able to have the computational resources to ensure that we capture all physical processes in our simulation technology that are not only confined to the reservoir, which is traditionally where a lot of the subsurface applications operate, but the whole of the subsurface, not only the injection layers, but also all the overburden that will provide the containment. And when you go into the specific of the site, then it's making sure that we are able to represent flow not only through reservoir layers, but also all the discontinuities. For example, faults that you see here in blue, and being able to have solver technology that allows us to model all these physical processes that we hope to monitor. And as you see, it's what we need to represent the subsurface as a whole. We can't necessarily borrow as is reservoir modeling technology as we see today, which is primarily fluid flow in porous media confined within the hydraulic unit of the reservoir, but the subsurface as a whole. And that puts even stronger, or that demands for stronger connectivity between all sorts of data types. And that's why, I mean, for the rest of the presentation, the only thing I just want to make is what is it that we need to do from a data type point of view to enable this sort of simulation technology in the cloud. And for that, I'm just going to make the argument that one of the things that we need is to liberate the information. And by that, we mean keeping the data alive, and that's just jargon for making sure that we're always working on the correct version of the data. As we know today, many of our engineers are working on different versions of the data, and that brings in efficiencies. Make sure that the data, we have a single version of it and it's discoverable. It doesn't exist just on the laptop of one of our engineers in one of my document layers, my document folders of a particular engineer that just might have left the company. And then once you have that transparent and accessible data, then build your software application so that it's designed from scratch to operate on liberated data. And this is kind of, as an example, just something like this, where today what we have is different subsurface integrity applications where we could try to model CO2 injection, for example, and then you have input data here, and then it's each user interacting with the data. What we want to do is actually rather decompose our applications into engines, which are liberating, taking advantage of cloud computing technology, and then try to avoid having the users, the owners of the data, but let the data live in data ecosystems that can be accessed directly from applications. And this is kind of the architecture of what's going to be needed if it is true that we want to reduce all these redundancies and inefficiencies in the data space, which are just one of the things that we would need to sort out as an industry if it is true that digital transformation is going to provide all those benefits for us. So once you have this data liberated, then you'll hear a lot this concept of data ecosystem. It's one of those buzzwords that are flying around boardrooms when we're talking about how do we digitally transform. And I just want you to remind you that data ecosystems are nothing more than just collections of liberated data. It's data that's georeferenced. It's data that has a lineage. It's tagged. You know who created it, and you have a very elegant way of managing the version of it. Then once you have that data with sufficient information for it to be discovered, then you just need to build applications that just knows where the data is. And it's not depending on user input for the data, but rather just leveraging all the metadata and georeferencing that the data may have just to operate over it. And one example for that in geomechanics is something like this, right? This is just one example where we have collected a lot of academic information and a lot of project information about in situ stresses, which is one of the variables that will really determine, for example, the stability of faults. It's going to determine something like the fracture gradient, which is that maximum pressure that you can achieve before fracturing the rock and having a leak of your fluids. And all that information can be stored in a single place, can be accessed, and that's in a blending, whether it's knowledge from reports, knowledge from academic sources, for example, like from the World Stress Map, and co-visualized. So just as a little example to finish off, um, here I'm just showing you one example of what that means in practice, just for a simple Excel spreadsheet, which is all how we as engineers work. And rather than saving that Excel spreadsheet and trying or avoiding the urge to operate on it yourself, you can put it into a data ecosystem. What you're doing here, I mean, the closest thing to those is just to quote unquote upload the data. But then the difference in this uploading the data is that the system needs to know or attempts to uncover where that data lives in geospace, pretty much. And what you see here, that data that you just put into the data ecosystem, the system understood where you were, or any information or metadata on latitude and longitude of that information, what type is it, and then what you're seeing here is something that not only you can access, but also that your peers or even partners in a venture can access. You see here that what we're doing is plotting stress direction, and it's because the system will see what type of data you loaded, and then it also, for example, knows how to render it. And then you can see stress information in the context of other academic sources like the World Stress Map, and you can see, for example, the data in context of other stress information that might be needed, but this time coming from geomechanical models that are built around drilled wells. And if you just want to see that, for example, the connectivity of the information of the data can already pinpoint you to the sort of applications that would consume that data, which is what you're seeing here. So we just clicked on the information, it knows what sort of software can operate over that data, and that just takes you directly to a particular app that can operate over it. So to finalize, as I said, the presentation was just trying to think about how if we tap into the current wave of digital transformation and we take the lessons learned of what we see in oil and gas for subsurface integrity, which is the closest mapping to what's going to be needed for safe CO2 storage, how we can, take those lessons learned primarily in the area of data liberation to make sure that we can scale subsurface integrity when it comes to managing all the requirements for CO2 storage that the decarbonization strategies globally are going to require going into the future. So with that, thank you for your time, and I think we can have some questions now.
Thank you, Adrian. Thank you for a very interesting presentation. Yes, we have a couple of questions for you. The first question is, are you aware of any CO2 storage project that is using real-time monitoring at the moment, and what their experience is?
Yes, I'm aware of a few. I'll tell you what, one of the things it's commonly monitored, and I think quote unquote real time, is microseismicity, and we see that. And what's real time right now is the collection of the information. I mean, it's easy to instrument. There's some sites that have been instrumented on surface and also on downhole in the boreholes. But you still see that even though you are the real-time monitoring the site, there's still a layer where you need a human to process the data, because there's a lot of pre-processing that happens in terms of automated picking of the largest events. But really to have a proper understanding, or you want to make a decision on the injection, whether to stop something or to actually raise a red flag, you won't do it with this basic pre-processing algorithm. So there's still a long way to go in terms of getting that information, say interpreting, for example, in the case of microseismic, to sufficient level of reliability that you understand what that event is. But microseismic, and yet again, alone doesn't really tell you much what to do. It doesn't really tell you what's happening or what caused it. You just see an event, you can raise a flag. So if I put that in context to what we want to do here, is imagine that that microseismic now exists as a digital event. How can you trigger downstream applications of that microseismic events to, for example, update your subsurface model so that given the conditions that you know you have, you could actually predict why is it that you generated that event. And those are when I made this comments about that there's still too many humans in between. I mean, obviously we're not going to get rid of humans. We want to get rid of humans in the button pushing of processing information or exporting from one location and loading the data in another application. And that's just a very good example. We can collect microseismic data. We still need some bits and pieces to process it with a human. And once it's processed, it still needs to be exported manually to some other application, to somebody to spend a month trying to understand what that meant from a geomechanics point of view.
Okay, thank you very much. And we have another one. Could you please elaborate on what is the engine behind that data liberation?
Yeah, so there's two things. Because of time, I didn't explain, but usually it's a couple of systems that you need, but there are primarily it's just two. One, there's the engine liberation concept, and the other one is the data liberation. So in terms of data liberation per se, it's not a single thing. It's just a framework. It's just a way of thinking of how data should be stored and managed in the cloud across, at an enterprise level. So in itself is not an engine. I did mention that there's this concept of engine liberation, and that is any numerical solver, the likes of which we used to use in today, but rather than it being designed to or assume that you're going to give it some sort of a input deck that lives in your machine, or that it's going to run in your machine unless you otherwise explicitly tell it that it should go to a particular cluster. How the software from the get-go is already designed so that the data that's going to consume, it's a data that's liberated. The HPC system that's going to run, it's something that you don't have to tell it. It already knows how to partition, how to access HPC compute power, and how to return the data in a way that it doesn't clutter your system, but it kind of knows how to update, register, and version the data. So the engine per se that we use in this case are finite element stress solvers, because that's a particular discipline, a particular state variable that we're interested in, which is in situ stresses. And we use finite element stress solvers for the domain problem. And what we are embarked at the moment, as you know, in a similar fashion as many are our peers in the company, is how do we make these engines that were traditionally built to run on a machine, how to modify them so that they're just running in cyberspace, accessing the data they need whenever they need it, and reporting the results where they should be reported.
And we have a lot more questions, but in the interest of time, I'm just going to ask the last question, and then I will reach out to the people with that couldn't answer the questions here right away. The question is, can NOAA specialists, mechanics use the information in the workflows to help enhance their decisions? For example, without your mechanical knowledge, if I see a graph of downhole pressure versus sanding probability, can I react to control my well flowing conditions to avoid the sanding without the need to understand the calculations behind?
I mean, that's a very interesting question. And I'll just use the opportunity maybe to kind of maybe recast that question into something more generic. But something that maybe I didn't have time to dive into too much is that when we were talking about data liberation and engine liberation, we were just talking one-to-one, as in for a particular problem, say in geomechanics, you can liberate your data because you want to deal with all the issues of versioning and inefficiencies of data storage, and have an engine that knows how to run over it. Now, that's only one aspect of it. Another of the vision of having these engines liberated is that then you can, as long as you establish the correct translation or the correct communication language between applications, it'll be much easier for different disciplines to communicate on a computational level. What does that mean? Today, if, for example, a production engineer would be interested in using some of the results from the geomechanics calculation, no matter how good the geomechanics analysis is, and no matter how good the production engineering software is, most likely the communication is going to be an email with some requests. So one of the things that we've been doing as well, and this is actually a very nice use case, is how drilling engineers, which may not be geomechanics experts, they're actually working in their cloud native drilling applications. And because we have the engine liberated, and because we've explicitly told the engine, hey, whenever you receive a request for information, this is how you should translate your engine results into variables that are of the understanding that speak the same language as a drill engineer. So for example, we might be using something like a principal minimum component of the stress tensor, and we know that that needs to be translated into fracture gradient. And then the curve goes in that sense. So for example, for sanding, we would expect, rather than the production engineer being the expert in geomechanics and sand production, we know that, hey, whenever a production engineering application is requesting a drawdown limit, most likely that's for sanding. So we take the stress information, we take the rock mechanics information, for example, the strength, we apply sanding models directly on the engine, and the data that just gets shipped is a translated version of that geomechanical information into the language of the production engineer. Why is this possible, or why we think this is going to be possible now rather than before, is that we try to minimize the amount of communication links that depends on humans, and that's where we get lost in translation, because you only have few individuals that are able to talk both languages, and then that's your bottleneck for scalability. So by removing that step, we let the engines communicate with each other, and then the engineers focus on the interpretation of the results rather than being, playing around in the logistics of the data.
Okay. Well, thank you very much, Adrian. That was very interesting. As I said, I will reach out to the people who I couldn't answer the questions here right now. And with that, let's continue with our second presentation. And basically, we're going to be having Maury Callander. He's the CEO of Eigen, and he will talk about taking the next step, turning decisions into action. Welcome, Maury, and thank you for attending.
Thanks very much. Yeah, very pleased to be here, and thank you, Adrian. So I'll just share, if you can make me a presenter again.
Yeah.
And we'll get this.
There you go.
I still don't have the share enabled. Now I do. Excellent. Okay. Hopefully you're all seeing the presentation. I'm going to take a little bit of time and talk about something we have called decision bridge technology. It's about taking the next step. I've got examples in this presentation. They're to do with the oil and gas industry, but they would be applicable to any other industry. So I'm just going to start off with a little story from my history, my embarrassing teenage years. This is the mighty Marshall JCM 800 amplifier. If anyone plays the guitar, you may know this amp. It's an amazing amp. It's a valve amp, so it's got a lovely sound. Well, when I was about 15, I went into a guitar shop to try out one of these amplifiers with a view to buying it. I did what every teenager at the time did, and I went in and I played some riffs, one of them being this riff by Sweet Child of Mine, the opening bars. And then the shop assistant came over and pointed to a sign on the wall that said, in no uncertain terms, anyone playing that riff would be forcibly removed from the shop. It also mentioned ripping their guts out and some other stuff. So I embarrassingly apologized and actually bought the amp and ran out the shop. So why do I tell that story? And thanks for the comment of someone who's got the amp still. It's a fantastic amp, loved it. But the reason is all I was playing was the riff. And the people in the shop got really fed up of hearing the same thing over and over again. And what we found is that there's certain things that we talk about in digitalization that are just the riff. And one of them is dashboards. So real musicians can play the whole song. So what do we mean by the whole song? Well, to deliver value, digitalization needs to help you take decisions faster and then take action on them. You need to get the whole way through the workflow. If you just talk about, say, a dashboard or one part of the song, you never get the value out. And Adrian mentioned earlier there that what happens in reality with the drilling engineers, they end up sending an email. Or it's people revert back to the same technology that we've actually been using for 30 years, which is Microsoft Office to run most things. So I want to talk today about 4 examples that help us to get to a decision and an action quicker. The first is, can we eliminate the copying and pasting of information from Excel and PowerPoint? Second is, can we help people avoid having to go into different systems to find out what the status of something is? Next one is, can we avoid sending email to the whole company? Like, can we avoid emailing a PowerPoint out every week just to keep people updated with what's going on? And the final one is, do I really have to manually create different versions of the same report every day? So the examples we're going to look at are often overlooked areas. They're not particularly complicated in many ways. I'd say they're the complete opposite spectrum of what Adrian was presenting. These are areas, though, where that we can digitalize them, we have done, and they deliver real benefits very quickly. Okay, so the first example I want to talk about is how we speed up the process of finding information to then creating something, a record of a decision, and then an action from it. So the objective here is, how can I easily record my findings and share them with others? Can we eliminate the need to copy and paste everything from some other system into Excel, screenshot it, put it in PowerPoint, and then send it out? So the situation we're going to look at is a typical thing where you have an engineer on an asset that needs to carry out some ad hoc investigation. They need to make a trend of something. When they found something, they need to record it, and then they need to share it with others. Previously, that would be copying and pasting it into Excel. What I'm going to show you, though, is that we can create our trend, but then with a click of a button, we can instantly then turn that into live content that we can share and interact with. Okay, so to start the demo off, I've lost my mouse pointer. This could be interesting. There we are. We've got a schematic of a well, and I'm just going to take a look at the wellhead pressure. Now, this is going to be a bit like the Blue Peter example, because there is one I prepared earlier. So we're going to look, just go back in time and see if there was an issue. I'm going to just look at a year's worth of data, and we do have a little issue here. Something happened here in our trend. So maybe I want to add on, say, another data series onto it. The choke position, say, looks like maybe we lost some data. Yeah, it looks like on this center we lost some data. So maybe I want to annotate that trend with the values, and then maybe I'll add a marker in there and say data log starts. And then I might add another one, but I'll show you one I made earlier. But just to get through this quickly, the key is I finished my investigation. Something happened here. I want to now share it with people. I click this button to create page. This then takes that trend I've made and puts it into a page that I can now work on. I can add comments to here. I can add comments. I can also share it with people. So if I click the share icon, I could share that with a colleague of mine. So then I can send it. They can now have a look at it and comment on it. And this was the one I made earlier, very, very similar. But you can see here, I just added a couple of markers to say this is, we lost comms to the wellhead pressure sensor. It came back again at this point. There was a comment on it by me in this case, but whoever I shared it with could still interact with this data if they wanted to. They could zoom in a bit further, or they could add stuff to it, or set it back. The page is fully configurable, so they could add more content if they wanted to. It's just go in and add sections and set the layout, add some text, whatever. So the key features of that was the decisions we accelerated were that we sped up the time between taking the decision and recording it. Our valuable, expensive engineers spent less time doing low value work and more time doing useful, important work. The actions taken were that we could then request information with others, and their input was tracked in a central location. We've got a record of all the discussions related to this event. We had a single click to create the new content. The content that we created is fully customizable, so we don't need to use Excel to make a report or make something look like nice. The data stay live and interactive, so it's not a dead file in someone's inbox. There's now a record of this, so it can be referred back to easily, and the organization can learn. And we've got rid of the low value copy paste work. Okay, second example. So the objective here is, how can I easily understand if there's actions on me and the status of work processes that I'm responsible for? Do I need to go into all the systems, like the maintenance system, the HSEQ system, purchasing system, requisitions? Do I need to go into all of those to find out what the status is? Or could it be that I could just have a single page that would show me? So the situation is that members of an operations team are responsible for responding to HSE actions, raising and reviewing work orders, requesting quotes from suppliers, and issuing contracts. This information is in at least 3 different systems, and they need to log in to each one to see the status. So what I'm going to demo here is an example where we've got some live information from a system. I can see a summary of stuff, and specifically I can click on the one of them that say is dependent on me or I'm interested in, and it takes me to the system where I need to complete that action. So the demo I'm going to show is just for one of our internal systems, but each table could come from a different system. So here we've got some live information from our support system. This is just tickets that we get in, and here we can see we've got them grouped by unresolved, some high priority ones. I can sort them, I could filter them on the ones relevant to me. And then here I've got some overdue tickets that I might be interested in. Now, if I click on one of them, that's one actually I don't have access to see. Interesting one is 9160. Let's try that one. Oh. Go to the different table. Ticket ID. No, where is that? Oh, there we go. So I click on it, and here it opens a ticket. This is one I'm able to see, and it just shows me all the data that's relevant to it. If I had an action, I could just go on and complete it then in that system. So that's an example of where it's a pretty straightforward thing, but what we've done again is we've just saved some time in an engineer's process of identifying where their input is needed and what needs to happen next. It lets them see if they're holding a process up or if one of their processes is being held up by someone else. So the actions they can take then is either to complete their action or to chase the person that's holding it up. It's live information. It's not replicated into our system. It's just a link to the source system. The layouts are completely customizable, and you can configure the on-click actions to determine what happens when you click on a field. And each table can come from a different data source. Okay, the third example I want to talk about is publishing information for shared awareness. So this is the objective here is how easily and regularly broadcast important information to all staff. Do I have to keep emailing a PowerPoint out? That's kind of the standard thing. You'll get something sent, say the HSEQ report or availability report. The example we were looking at that we helped a customer with was the rapidly changing situation around coronavirus. Offshore, that meant changing shift patterns. There was lots of people who needed to be kept up with what was happening. The latest information on safety procedures and even things down to who could go to the canteen when was literally changing daily. The standard method was to email around a PowerPoint, but was there a way to actually make this much more immediate and remove the inbox clutter and the need to email it around? What we have is a technology called Screen Presenter. It takes content, PowerPoint or other web pages, and it puts them in a slideshow, just cycles around itself. So you might say, well, how's that different from putting on the internet? The difference here is a key difference is the user doesn't have to scroll through anything. It cycles through information on a screen so it can be put in a public display. It's available on a URL so anyone can look at it. But if you put it up in, say, a public area where no one can access a mouse or scroll through stuff, someone just has to stand there and watch the screen, and all the relevant stuff will just cycle through and they can see it. It takes information from a folder, so it's so simple to update. All you need to do is put a new file in that folder and it will be included, or you can remove one and it'll be gone. So let's have a little look at what that looks like. Here, so what you'll see is the screens that I had in that PowerPoint, they'll just cycle through. This is the list. That looks pretty big. I'll zoom out a bit so you can see it. This is the set of screens that we have. These are ones that we've made for this demo that we're interested in for us. And you can see that some of them come from other websites. So there's just a URL, and that in a text file that gets incorporated in the slideshow. But then some of them here are images that are exported from the PowerPoint. So there's nothing complicated for users. No one needs how to make web pages to make something appear. All they need to know how to do is to either paste a URL into a text file or drag and drop an image into a folder. You can see also that the duration of each screen is customized. You can just set it by writing something in the file name. If there's nothing there, it will just default to whatever's configured as the default. And it also intelligently zooms the pages so that they fit on the screen. So it's a URL, but the content that you're seeing within that is just changing. Okay, so what decisions did we accelerate? Well, we helped the understanding of the latest COVID-related procedures. And actually, that was just one example. The company uses it for many other things, including publishing weekly HSE reports. The actions it enabled was the immediate publication of new information. When you send a PowerPoint that's maybe gigabytes, people actually get fed up if you send that regularly. So if something changed, people are thinking, do I have to send out another 10 megabytes into someone's inbox? There's a reticence to send it out, even though it's important information. And it also might be missed, because how do you know what the latest version of stuff is when you have so many copies? It meant it was much easier to know what the latest procedures are, so the level of adoption was much higher. The workflow of the tool is dead simple. It's literally just drag and dropping stuff into a folder. You can include web pages from other systems. The URL can be accessed by anyone internally, and you get instant updates on it. Okay, the last example I want to look at is publishing of a weekly KPI report. So how can we reduce the time it takes engineers to produce the plant availability report? Do they have to do it manually in PowerPoint every week? So plant availability reports were created manually by the reliability report every week in Excel. This involved a lot of copy and pasting of information from different systems and then pasting it into PowerPoint. This takes a lot of time and it's also prone to errors. Adrian mentioned this as well, that the more humans touch data, the less veracity it has, the more likely we are to introduce errors. And it just puts the cost up of producing that report. So what we have is a system that automates the data capture and then generation of regular reports. People can make the reports just like I showed you at the start, where you can make trends. Instead of making reports in Excel, they can be made in our web environment. You can have tables, text entry, KPIs, charts, the whole lot. And then by adding a component at the top, it turns it into a template. A template allows you to specify different versions of that content. So you can take a template and generate multiple different versions of the report. For example, an internal one or an external one for different audiences. So let me show you what that looks like. Yeah. Oh. So here we've got the template for the morning report, and this is the component you can see at the top that lets me select the time when I want to produce it. I have a number of different components on the page. Oh. And you can see here I've got some KPIs, I've got a table of information, I've got some charts, and also I've got some manual entry. So people, when they collaborate on the meeting, can actually type text directly into the report. To collect the data, all I need to do is to set the date. So let's create one for today. Just check I haven't already made one. No, I haven't got. So we just set the date and it's updated all the content in the report with today's data. When I'm happy with the content, I just need to click create. And that will go and create the different versions of that report. So we can see here, I've got one for offshore. I've also got one head office. And I've also, so offshore head office, offshore again, September. So I'll show you the difference in the content. The offshore one that you can see here has the KPIs at the top. It has a table of information and something on critical equipment. But if I go to look at the head office report, you'll see that it's missing some of the other content, but it has other content. So for example, it has these bar charts in there. The way that we're able to do that is by tagging the components with what, so for example here, this component is tagged with the head office offshore report, will appear in both. But this chart component here is only tagged with the head office report. So you can create as many different versions of that report as you like, and each version can have its own distribution list. So when I go to the setup report here, you can see on the under here, the recipients, I can set my distribution list specific to the version. So what this let us do is remove all the manual processes around the morning report, but the people still meet to discuss the data. So all the valuable stuff still happens in very much the same way that it did, but we've sped up the data capture process and the data sort of manipulation and distribution process. Again, it's all automated. So we're using our people for their most valuable thing. So just to summarize there, that we sped up the time to generate the report by about 3 hours a week. It's about 30 minutes a day for an onshore production manager. 6 days a week gives you 3 hours. The report was issued in less time with consistent quality. There's no copy-paste errors because it's all automated. And so those resources now have more time to focus on other activities. We converted what was a complex Excel and PowerPoint process into just a simple online report. It's a couple of clicks of the button and any manual text entry if you want it. There's a full history of all the previous reports there online that people can access. And we also have version control templates, so it's very easy to see if someone's changed it or roll back to a previous version. So that's in summary. We did manage to eliminate the tedious copy pasting and speed up the collaboration. We were able to make it possible such that people didn't have to go into different systems to understand the status. We've shown that it was possible to communicate within an office faster and replacing the tedious email PowerPoints. And we also showed it's possible to remove the frequent manual activities around regular reporting and improve accuracy and reduce wasted time at the same time. So, any questions?
Thank you, Murray. That's it looks like a very versatile technology. And yes, we have a question for you. Could you apply this technology for the optimization of other energy sources like wind power?
Yes, absolutely you could. The system is completely agnostic as to the industry it's in. It's just anywhere where you've got industrial workflows that involve the collaboration of people around data from systems, and specifically industrial systems. So where you're doing things like sensor data combined with maintenance data. So systems of records, real-time data, also static reporting type stuff.
Good. All right. Well, I think we are reaching the end of the webinar. I want to thank you all for your participation, and we hope you find it useful and informative. Thanks again to our panelists, our guests tonight. And if you have a story related to energy systems and digital technologies and would like to share it with the Energy Institute community, please do get in touch. We'll be happy to hear you. So have a good evening, and I look forward to seeing you again next time. Thank you.
Thank you.
Thank you.
Bye-bye.
Bye.